Welcome back to Code Wonka. Today we will be solving lead code problem HouseRobber. We will start by brute force solution and build our way towards optimal solution. Let's go over the question. You are a professional robber planning to rob houses. Each house has a certain amount of money stashed. The only constraint stopping you from robbing each of them is that adjacent houses have security systems connected, and it will automatically contact the police if two adjacent houses were broken into on the same night. Given an integer array nums representing the amount of money of each house, return the maximum amount of money you can rob tonight without alerting the police. So from reading the question, the only constraint we have is that we cannot rob adjacent houses, and goal is to maximize the rob amount. Let's take this example test case to understand the problem better. The expected output of this input array houses is 12 because the maximum amount that can be robbed without robbing adjacent houses is 2 plus 9 plus 1, which is 12. Let's think about a solution to the problem. Let's say we are at house at index 0. The only two actions we can take is to either rob the current house and move to house at index plus 2, or we can skip robbing the current house and move to next house at index plus 1. Let's say the rob amount is initialized to 0 and we are at index 0. We want to take the first action of robbing the current house. Let's visualize this action. We rob the current house by adding the house amount to the variable rob amount. So the variable gets updated to 2, and we move index pointer to index plus 2. Now let's say we are at index 0 and now we want to take the second action to skip robbing the current house. Let's visualize the second action. The rob amount will be unchanged, which will be 0, and we will simply move the index pointer to the house at index plus 1. These two actions that we discussed can be easily incorporated using recursion in code, where we will have two recursion call, one for taking the current house rob and second for skipping the current house rob. Let's code the solution. We define the inner function recurse, which takes index as input. Then we take the first action to keep the current house rob. We do this by recursively calling the recurse function with input index plus 2, and we add the amount of house at current index to it. Next, we take the second action to skip the current house. We do this by recursively calling the recurse function with input index plus 1. Then we return the maximum amount that we get by keeping the current house rob and skipping the current house rob. The base condition will be if index is out of bound, then we return the amount 0. At the end, we return the output of recurse function with input as index 0. The time complexity of the code is O of 2 raised to n because the function calls itself 2 times, one for taking the rob and second for skipping the rob. The space complexity is O of n because of the storage by recursion stack. Let's look at the recursion tree of the brute force approach and think of optimizing the solution. All the right nodes are result of robbing the house at the parent node. All the left nodes of the tree are result of skipping the rob of the house at the parent node. The node values represent the input of the recurse function, which is index. If you observe, we are calculating the maximum rob amount at index 2 times. So we are doing some recomputation over here. We can optimize the solution by storing the computation of the first visit to index 2 in the cache. And we can avoid the recomputation of the next visit, red colored node 2, by taking the rob amount from the cache. So the blue circled subtree will get pruned. We can do this in O of n solution by using memoization. Memoization is cache on top of recursion. So to the original recursion code, we add these 4 lines. Let's look at these code lines one by one to see how the time complexity is reduced from O of 2 raised to n to O of n. We create a cache called memo, which is empty dictionary. Next, we store the maximum rob amount at current index in the cache memo, and we return the value of the maximum rob amount from this cache. We add another base condition where if we have already visited this index before, then we have its entry in the memo dictionary. We don't need to recompute the maximum rob amount at this index because we can reuse the maximum rob amount at this index from the cache memo variable. This way we reduce the time complexity to O of n. The time complexity is O of n because we visit each index only once. We avoid revisiting the index using the cache memo variable. The space complexity is O of n because of the recursion stack and the storage by memo variable. Now let's talk about optimizing the space of the O of n solution. To optimize the space, it's important that this additional intuition comes in your thoughts, where we keep track of maximum rob till current index. This bottom-up intuition idea can be drawn by reversing the top-down memoization solution, where we keep track of maximum rob from current index. Let's say we are at index 2 and we somehow already calculated the max rob till index 0, that is 2, and max rob till index 1, that is 7. How did we calculate this? We will look at a later point when coding the solution. Now if we were to determine what will be the max rob till index 2, then intuitively we will take the maximum amount of the 2 action, that is to either rob the current house or skip the current house. This operation can be represented by this calculation. In the calculation, robbing the current house condition is highlighted in blue, which is max rob till index minus 2 plus current index house amount. And skipping the current house condition is highlighted in red, which is simply the rob till index minus 1. So the answer will be 11. We fill the index 2 of max rob till index array with 11 and move the index pointer to index plus 1. We fill index 3 of max rob till index array with same calculation, where we take the max rob amount from either robbing the current house or skipping the current house. The max rob will be 11. We fill 11 at index 3. We move index pointer at 4. We do the same calculation to take the current rob or skip the current rob, and we get 12. We fill index 4 with 12 and return it. If you observe, at every index we were using only 3 pointers: max rob till index minus 2, max rob till index minus 1, and max of skipping the rob and taking the rob. So we can replace max rob till index array with these 3 pointers, which will optimize the space to O of 1. Let's code the solution. Line 3, we initialize max rob so far to 0, which represents max rob amount till current index. At line 4, we initialize max rob till previous index to 0, which represents max rob till index minus 1. At line 5, we initialize max rob till before previous index to 0, which represents max rob till index minus 2. Next, we write a for loop to iterate through each and every house in the houses array. Next, we compute the rob amount from action to take the current house rob amount. Next, we compute the rob amount from the action to skip the current house rob amount. Then we take the maximum amount from the 2 actions, that is to either take the rob amount or skip the rob amount, to determine the max rob amount till current index. Then we update the max rob till before previous index to max rob till previous index, and we update max rob till previous index to max rob so far and return max rob so far. The time complexity of the code is O of n and space is O of 1. Please leave your feedback about this video in the comment section. If this video helped you in learning, then please subscribe to the channel and hit like button and share it with your friends. Thank you for watching this video and stay tuned.